Hello, everyone. Welcome back to our second half of the lecture. We already talked about the basics of sound waves. So to introduce you with the concept of the physics of sound waves, I want to briefly recap what we just went through using these slides. This slide is made by actually Professor Tamara Smith in her class Music 171. Okay, this is the first lecture class, so yeah, first lecture slides. So don't worry, it won't be difficult. Just introduce some basic concepts, and most importantly, introduce you with the sinusoidal model of sine and cosine. Okay, some basic numerical relationships and the physical concepts. After that, we will proceed with the with equations. Okay. So let me recap this again and to reiterate and make sure you have a more complete, better understanding of what we just went through using the YouTube videos. Okay. So what is sound? An auditory sensation in the air. Okay. From something that vibrates, so the disturbance in a medium that causes an auditory sensation. So nearly all objects will vibrate when disturbed. Sound is a wave created by vibrating objects, alternating regions of low and high pressure that propagate through a medium from one location to another, right? So this is what the sound wave is. The basic definition. And sound wave, we talked about the sound wave is a mechanical wave, right? It requires a medium in which to propagate, be air, liquid, or solid. Okay, so in different medium, the waveform propagates at different speed. And if there's no medium, there will be no sound, and the sound won't propagate. So this is a mechanical wave in the definition. And sound is a traveling wave. Okay, we didn't talk explicitly talking about traveling wave. A traveling wave means it propagates from one location to another, right? It's traveling in space. So the particles don't travel, only the force or the motion will travel through those particles in this medium that travels far. Okay, so sound is a traveling wave. It propagates from one location to another. In fluids, like air and water, sound is a longitudinal wave. It has alternating regions of low and high pressure. So the regions of high pressure is called compression. The regions of low pressure is called rarefaction, right? And in most cases, sound is longitudinal wave. But in order to depict this more clearly, right? Because if the particle is moving at the same direction as the sound wave, it's difficult to draw it on a plain paper. Okay, so we only have a two-dimensional plain paper. We want to draw the movement of the particle. Usually, we draw it as a transverse wave, like here. Okay. Let me get this annotation here. So here is the direction the wave travels, okay? And this is the direction of the particle movement, okay? So they are perpendicular to each other. So this is a transverse wave. So in reality, the sound is longitudinal wave, but for convenience, we just draw it on the paper as longitudinal wave, as transverse wave, sorry. Okay. So the waveform illustrates the pressure variation of the wave. So next is the wavelength. Okay, so for waveform, the wavelength is defined by the crest, the two crests of the wave. So the distance between the two crests is the wavelength. So wavelength, we usually use lambda. Okay, use lambda to represent wavelength. So the wavelength is the length of one cycle. The distance between crests or between the between the troughs, it's the same, okay? It's the same distance here. So usually we just, for convenience, we see this is distance between two crests. And waves are often characterized by their length. The different waves have different length, right? The wavelength here. So they have different wavelengths. Some waves are like this, right? So they have like much longer wavelength, but some waves, so they have higher frequencies, so they have a smaller wavelength here, right? So different waves are characterized by different length, and for our visual system here, so this is in this very narrow range is the frequencies that we can see, okay? So the wavelength between 400 and 700 are the visible wavelength we can see, right? In different colors. So this is where color comes from. So in the wavelength below this range is called ultraviolet, X-rays, and gamma rays. And here, above this visible range is infrared and microwaves and radio waves. So we cannot see those waves, but we use these waves all the time in our real life, right? Like X-rays is like ultra violet, and micro. Oh, sorry, I said. Yeah, this is right. This is right. So the wavelength is much shorter, but the frequency is higher. Okay, so remember, the relationship between the wavelength and the frequency is inverse proportional. Okay. So okay, let me illustrate this. So wavelength, right, is the length is given by the c is the velocity, t is the time, okay, is the period. And we know that the c, the velocity, is given by the transmission medium, right? Like in the air, we have 340 meters per second. So this is c. So c is given, is fixed, and t is the relationship between t and the frequency is that, right? Inverse proportional to t is the 1 over frequency. Therefore, when this is a constant, the relationship between here, right, between the wavelength is inverse proportional to the frequency. Therefore, we can see that the X-rays, the gamma rays, so they are of highly damage, right? They have they are very dangerous. These dangerous things, they are of this very, very short wavelength, but they have high frequencies. So we see the high frequency waves are actually dangerous, right? But for those waves, they have longer wavelength, which means they have lower frequencies. So they are used in in the microwaves to heat, or the radio waves, right? The radio waves we just receive and listen to the radio broadcast. So this is the basic range. Sorry. Of these. So there are infrasonic, lower than lowest audible frequency, and ultrasonic. So I don't know why it's given by the visible thing. Okay. So here it's more fundamental concept on the waveform, okay, period and the frequency. So we already know period is given by the two crests, the distance between the two crests, but here the x-axis is time, right? We said when the x-axis is time, the distance between two crests is period. However, let me clear this. However, here, when this x-axis is the position, right? This distance between two crests is wavelength. And here, because in this graph, the x-axis is time. Therefore, the distance between two crests are period. Okay. So if we know wave velocity, which is the speed, right, we can determine the period from the wavelength. So the period is usually, we see is t, right? Period is given by t, and the wavelength is lambda, and the velocity is c. So this is the mathematical notation we usually use to describe those quantities. So this is how we compute t from lambda, from the wavelength. And t is also the inverse of frequency, right? So the frequency is the number of cycles per second. And this is the inverse of the period and the inverse of this expression. Any questions so far? If anything is not clear, I can give more time to explain them. Okay. So for waveform, the temporal waveform of the sound shows the time evolution of the pressure variations, illustrating the amplitude, period, frequency, and wavelength. So what are those terms? So here gives the property of sound waves. Okay, so we already talked about the different speed of sound waves in different transmission medium. So in air, it's this number 340 meters per second. In water, is much faster, and in solid, it's even faster. It's like it reaches like 3 kilometers or even 5 kilometers in steel. So amplitude range of hearing. So it's somehow related to psychoacoustics, which we will address in week 4. But here it provides the amplitude range of hearing. The threshold of audibility is, this number of is the Pascal, is the pressure. The measure of pressure, threshold of feeling or pain is 200 Pascal. The frequency range of hearing, okay, in many videos in previous materials, is talk about our human hearing range of frequency is 20 to 20,000 hertz. Okay, this is our audible range. It is band limited, right? It's band limited. The highest frequency we can hear is 20,000 hertz. This is also why the digitalization of sound doesn't really, damage or influence the sound quality, right? So we'll talk about this later on in our next week. But here is just a brief. I just briefly address the range of frequency hearing. Okay, the highest frequency is to 20,000 hertz. So dogs, they have a larger frequency range of hearing, so they can hear sounds like up to 45,000 hertz. Therefore, if you think about this, so when you play a sound that's recorded by viol, by viol and recorded by the computer, so human will hear the same sound, but if you play this to the dog, it will hear different sounds, probably. Okay. So because they have a larger range of hearing, and the whale have a different range of hearing, a period of lowest and highest audible frequencies. And this is just some basic, mathematical operations. I will skip this part. And you can see the shortest human audible wavelength is 1.7 centimeter, and the longest is 70 meters. So why sinusoids are important? So many models actually described by sine and cosine waves. So it gives some explanation here why we study sinusoidal model explicitly, but basically it's because it's easy to manipulate mathematically. So in nature, in real nature, there's no pure tone. So none of the instruments or none of the sound we hear from nature is a pure sinusoid. Is of this form. Okay. None of the sound is of this form. So every sound is a complex tune. It's superposed by those different, harmonics, different sinusoidal waves. Because in the sinusoid wave can serve as a basis, which means all the sound waves can be decomposed into the combinations of sine and cosines. And this is easy to manipulate. And if we have time to talk about complex numbers, these are the fundamental components that we will use dealing with the complex numbers and in Fourier transform and everything. The sinusoids are just easy to, easy to compute, easy to transform. And if you perform some mathematical or digital operations, it's the easiest model to study. Therefore, we will go through those basic concepts or basic, quantities here. So A is the peak, this is the amplitude, omega is the radiance or the radian frequency. And F is the frequency. We talked about T is time, phi is the phase. So this is the basic expression of sinusoids, okay, of a sine function, and this is the cosine function. And this is of the form like this. So we will see this wave form many times in this lecture. And also, if you take any course related to audio signals, this is the form you will see most of the time. Okay, the sinusoidal model. And in this waveform, you can see the A is 2, the amplitude is 2, right? So here is 2 minus 2. This is the vertical or the range of the amplitude. Okay. And omega is 2 pi here. And the phi is pi over 4. Okay. So we will talk more about this in the next slides. Cycle and initial phase. So one cycle of a sinusoid is 2 pi radians. Okay, so you can see here it describes this use. So this is one cycle, and one cycle is 2 pi. So why is 2 pi? It's actually the shape of the of a circle, right? When you have a circle, okay, let me use this. Sorry, should be this one. Clear drawings. Okay, so if you have a circle, the radius is 2 pi. If you go through one cycle on this circle, okay, this is why this is in this form of 2 pi. Okay. Or a cosine function is of this form. Okay, this is a sine function. This is a cosine function. Okay, so the sine function starts with 0. Okay, when the position is 0, and the cosine function starts with when the amplitude is the highest. Okay, it starts with if the amplitude is 1, it starts with 1. So when the amplitude is the highest, it is a cosine function. The initial phase is the phase at the time 0, and is phi pi between pi and pi, or phi between 0 and 2 pi. So initial phase phi actually gives the position of the sinusoids. Okay, so for a sine function, the phi is 0, which means it starts from the 0. Okay, the x and y both are 0. And in cosine function, when the phi is pi over 2, which means it starts with the highest amplitude. Okay, so this is only the transposition of these sinusoids, okay, like left and right. So when you transpose this to left and right, it gives you different phases. So here, I talk a lot about sine and cosine. When we talk about the standing waves, so the waves produced by the musical instruments, we'll go back to these concepts and investigate further on how these waves are produced on different instruments. and the relationship of upper harmonics. So frequency, hertz and radians. Okay. So frequency is inverse proportional to a period, it's 1 over t, and omega is 2 pi f. Okay, it's 2 pi times f as the frequency. So this is called the radian frequency. So there is a 2 pi in front of f. Okay. So in this wave shape, we can see, so let's do some basic calculation here to familiarize you with the concept. So here you can see so this is time, right? From 0 to 1, this is 1 second. And this is the length. Okay, so you can see the wave actually goes through 2 cycles here, right? 2 cycles in 1 second. Therefore, the frequency is 2 hertz, right? The frequency is 2 hertz because it goes through 2 cycles in 1 second, and the period is 1 over 2 is 0.5. Okay. So it takes 1.5 second to go through 1 cycle. So this is the 0.5 seconds is the period. And with the frequency in radians, so because the frequency f is 2, therefore omega is 2 pi f, right? And therefore it is 4 pi. Okay. I'm not writing really well here, but this is 4 pi of omega. Okay. So sine and cosine functions, the relationship between sine and cosine is just transposition. Okay, you just move the sine function maybe to the left for for pi over 2, and then you get the cosine. Okay, or if you think about this, when you cut from the sine wave, so this is sine wave, right? In these dashed lines, this sine wave starts from 0, and if you move it to the left for this distance, you'll get a cosine wave, right? It starts when t is 0, it starts from here, where it reaches the largest amplitude. Okay. So sinusoid model will be fundamental to study all the concepts like the physical model we're going to talk about this week, and also some of the Fourier transform next week. And we'll discuss the basic behavior of sound waves. Okay, the sinusoid model is always the thing that people employs, although it's just a mathematical model, which means it's not the reality. Okay, the reality, the real sound in the nature is never a pure tone. It's more complex. Yeah. So I will finish this here, and I hope this recap can give you a better understanding of those numerical relationships of the quantities. And since we already went through all those basic concepts of sound waves and everything, I think it's time to go through something. A basic question is that how do we describe the sound wave physically, right? So we know the sound waves are, sorry. Let me see. We know sound waves is of the shape like this, right? This is just random, and you cannot really see anything like quantitatively or determine what it is. So one way is that we just transform it to the frequency domain using the different frequencies, right? Different pitches to describe this sound, but from a more like fundamental concept, but how this sound is made, right? There is always a source, a sound source that creates those waves, and this wave propagates through the transmission medium like the air. But what's the behavior, what's the motion of this, and how do we describe this motion? So using a physical model to describe the sound from its source, we have to understand the partial differential equations. Okay. So why? Because in the previous slides, we already know that in order to describe sound, there are two variables, right? The two variables, one is time, which like gives here for a fixed particle, as the time goes by, it will oscillate, right? So the one of the variable is time, and another variable is position, is x. So for any given time, like we take a photo or a snapshot, this picture gives us what the position all those particles are, right, in this given time. So there are actually two variables to describe sound waves. Therefore, to describe the motion or the change of the waves through time or through the space, we need to invent, or we need to devise an equation y that is of the variables t and x. Okay, so this function actually has two variables, the time and the position. And why we need to use differential equations? Because we want to describe the changes, right? The change of time, and like how this particle is moving from time t to time t plus delta t. So there, in this very small, very small interval of time, what's the change, right, of the particle? And this describes the motion of the particle, and also from x, from this position to a very near position like x plus delta x. So what's the change of the movement of these two particles? So they are close to each other. I know it's not a really precise explanation why we need to use using differential equations, but this is the model that people use, okay, to describe like acoustic phenomenon. Okay. And also, so also here in our module this week, if you have an interest going through some advanced readings, especially this one, like the acoustics, you'll see in order to describe those acoustic model, they start with partial differential equations, everything partial differential equations. Okay, so you don't need to have you don't need to really master those concepts, but I think it's a good introduction. At least the concepts, like how people do this thing, and how the motion of waves can be described precisely. Here is a really good video that illustrates what is partial differential equations. So we will watch this together. So in this video, they use this heat equation of this form. Okay, this is not a wave equation. It's a heat equation. It's another type of partial differential equation. But the basic concept here, especially when this video describes the change through time, the change through the space, it is the same as what we describe wave equations. And after watching this video, it will give me a better foundation for me to introduce you how do we derive wave equations, and how do we solve the wave equations, and how do we apply those concepts to the phenomenon, okay, of the musical instruments. So let me play this. Okay.
After seeing how we think about ordinary differential equations in Chapter 1, we turn now to an example of a partial differential equation, the heat equation. To set things up, imagine you have some object, like a piece of metal, and you know how the heat is distributed across it at any one moment. That is, what's the temperature of every individual point along this plate? The question is, how will this distribution change over time as the heat flows from warmer spots to cooler ones? The image on the left shows the temperature of an example plate using color, with the graph of that temperature being shown on the right. To take a concrete one-dimensional example, let's say you have two different rods at different temperatures, where that temperature is uniform along each one. You know that when you bring them into contact, the temperature will flow from the hot one to the cool one, tending to make the whole thing equal over time. But how exactly? What will the temperature distribution be at each point in time? As is typical with differential equations, the idea is that it's easier to describe how this setup changes from moment to moment than it is to jump straight to a description of the full evolution. We write this rule of change in the language of derivatives, though as you'll see, we'll need to expand our vocabulary a bit beyond ordinary derivatives. And don't worry, we'll learn how to read the equations you're seeing now in just a minute. Variations of the heat equation show up in many other parts of math and physics, like Brownian motion, the Black-Scholes equations from finance, and all sorts of diffusion, so there are many dividends to be had from a deep understanding of this one setup. In the last video, we looked at ways of building understanding while acknowledging the truth that most differential equations are simply too difficult to actually solve. And indeed, PDEs tend to be even harder than ODEs, largely because they involve modeling infinitely many values changing in concert. But our main character for today is an equation that we actually can solve. In fact, if you've ever heard of Fourier series, you may be interested to know that this is the physical problem which babyface Fourier over here was trying to solve when he stumbled across the corner of math that is now so replete with his name. We'll dig into Fourier series much more deeply in the next chapter, but I would like to give you at least a little hint of the beautiful connection which is to come. This animation you're seeing right now shows how lots of little rotating vectors, each rotating at some constant integer frequency, can trace out an arbitrary shape. To be clear, what's happening is that these vectors are being added together, tip to tail, at each moment. And you might imagine that the last one has some sort of pencil at its tip, tracing a path as it goes. For finite...
Wait, I will skip this part. I think he's talking about the Fourier series, which we will talk about actually next week or next week. We talk about Fourier transform, okay, in more details. So here, probably let me skip this part and go to the changes. So why we use partial differential equations and how the equations are devised. Okay.
Labeled with a unique number, x. The temperature is some function of that position, t of x, shown here as a graph above it. But really, since the value changes over time, we should think of this function as having one more input, t, for time. You could, if you wanted, think of this input space as really being two-dimensional, representing space and time together, with the temperature being graphed as a surface above it, each slice across time showing you what that distribution looks like at any given moment.
Okay, so here you can see it's the same situation as in waveforms, right? You have two variables, which is time and the position. So you have, so all those particles, they change through time, right? The particles at different positions, they change through time.
Or you could simply think of this graph of temperature changing with time. Both are equivalent. This surface is not to be confused with what I was showing earlier, the temperature graph of a two-dimensional body. Be mindful when you're studying equations like these of whether time is being represented with its own axis, or if it's being represented with literal changes over time, say in an animation. Last chapter, we looked at some systems where just a handful of numbers changed over time, like the angle and angular velocity of a pendulum, describing that change in the language of derivatives. But when we have an entire function changing with time, the mathematical tools become slightly more intricate. Because we're thinking of this temperature function with multiple dimensions to its input space, in this case one for space and one for time, there are multiple different rates of change at play. There's the derivative with respect to x, how rapidly the temperature changes as you move along the rod. You might think of this as the slope of our surface when you slice it parallel to the x-axis, or given a tiny step in the x direction and the tiny change to temperature caused by it, this gives a ratio between the two. But there's also the rate at which a single point on the rod changes with time, what you might think of as the slope of the surface when you slice it in the other direction, parallel to the time axis. Each one of these derivatives tells only part of the story for how this temperature function changes, so we call them partial derivatives. To emphasize this point, the notation changes a little, replacing the letter d with a special curly d, sometimes called del. Personally, I think it's a little silly to change the notation for this, since it's essentially the same operation. I would rather see notation that emphasizes that the del T terms up in the numerators refer to different changes. One is a small change to temperature after a small change in time. The other is a small change to temperature after a small step in space. To reiterate a point I made in the calculus series, I do think it's healthy to initially read derivatives like this as a literal ratio between a small change to the function's output and the small change to the input that caused it. Just keep in mind that what this notation is meant to encode is the limit of that ratio for smaller and smaller nudges to the input, rather than a specific value of the ratio for a finitely small nudge. This goes for partial derivatives just as much as it does for ordinary derivatives. The heat equation is written in terms of these partial derivatives. It tells us that the way this function changes with respect to time depends on how it changes with respect to space. More specifically, it's proportional to the second partial derivative with respect to x. At a high level, the intuition is that at points where the temperature distribution curves, it tends to change more quickly, in the direction of that curvature. Since a rule like this is written using partial derivatives, we call it a partial differential equation. This has the funny result that to an outsider, the name sounds like a tamer version of ordinary differential equations, when quite to the contrary, partial differential equations tend to tell a much richer story than ODEs, and are much harder to solve in general. The general heat equation applies to bodies in any number of dimensions, which would mean more inputs to our temperature function, but it'll be easiest for us to stay focused on the one-dimensional case of a rod. As it is, graphing this in a way which gives time its own axis already pushes our visuals into the third dimension. So I threw out this equation, but where does this come from? How could you think up something like this yourself? Well, for that, let's simplify things by describing a discrete version of the setup, where you have only finitely many points x in a row. This is sort of like working in a pixelated universe where instead of having a continuum of temperatures, we have a finite set of separate values. The intuition here is simple. For a particular point, if its two neighbors on either side are on average hotter than it is, it will heat up. If they're cooler on average, it'll cool down. Here, specifically focus on these three neighboring points, x1, x2, and x3, with corresponding temperatures T1, T2, and T3. What we want to compare is the average of T1 and T3 with the value of T2. When this difference is greater than 0, T2 will tend to heat up. And the bigger the difference, the faster it heats up. Likewise, if it's negative, T2 will tend to cool down, at a rate proportional to that difference. More formally, we write that the derivative of T2, with respect to time, is proportional to the difference between this average value of its neighbors and its own value. Alpha here is simply a proportionality constant. To write this in a way which will ultimately explain the second derivative in the heat equation, let me rearrange this right hand a bit in terms of the difference between T1 and T2 and the difference between T2.
Okay, maybe let me stop here. I think the basic thing I want you to understand is this graph. Okay, is this graph with two variables, time and x, and the partial derivatives describes the change. Okay, the rate of change either through position or through time. Okay, so for the rest part, the author actually is talking about how to derive the heat equation. Okay, using the basic concepts, and which is the exact thing I will do in terms of the wave equation. Okay, so the derivation of wave equation. So this is the description of wave equation. Okay, let me don't use this. So there are many ways to derive the wave equation here in this form. There are stream model. Let me open this. So there's a stream vibration, and here is the stream model. How to derive this formula? Okay, using a lot of approximations, sine, cosine, and there's a tension, force, etc. So we're not going to go through the details, but the basic idea is that you pick a small part of this, and you do a physical model analysis of this force, and using the Newton's second law, F equals ma. Okay, and do a lot of approximation. Then you reach this form. Okay, this form is the wave equation. So this is the second partial derivative of x here, and this is the second partial derivative of t here. Another model is the used spring model. So here, so this is the form of wave equation, right? So in the derivation, using spring model is actually use the Hooke's law. Hooke's law is F equals kx, right? F equals kx. Therefore, they can write out the F here as k as the k times the distance, okay, of the position, and then doing some algebra, you can arrive this expression, etc., etc. Yeah, and you just reach this expression of wave equations. Okay, so if you are into those physical models, I really recommend you to read into those things. These only require high school physics. Yeah, the high school physics also introduced this F equals kx, right? The Hooke's law. And some partial differential equations might be yeah, the first year of college math. But here, since we don't have it's not a math course, so I'll give you an intuitive induction of this, so which won't be precise but will be intuitive for understanding. So before, in our last part, we talked about that there are two properties, right, of the mechanical waves, which is elasticity and inertia. So elasticity means there is a force to resist distortion. Okay, so we are going to use this elasticity of the material. So here we have a string, right? The string is somehow deformed, therefore it has a tension. Okay, let me use the annotation here. So here you can see there are tension at both the sides, right? T is the tension, is the force at both sides. T here and here. So here, I'll give you an intuition is that, so we know that F equals ma, right? This is the Newton's second law. M is the mass, right? So this M is a constant, so we don't care about this. And A is the illustration, which is the second derivative, okay, of time. So ut, so the first derivative is velocity, the second derivative is this acceleration. So this is the form we get, right? So, and this is actually this part. So this is this is A, right? C is constant, and now we only need to derive what is this expression. So what is force here? So actually, when the string is somehow deformed as this, for example, let's use our sinusoidal model here. Okay, like a sine wave, it is of the shape like this, right? So what's the force? So we know this, let's say it is a string, so that it has this elasticity. It resists the deformation. So here, so at first this string will be flat, okay? The string is flat. This is its initial position. And now you are actually plug this string or drag this thing up. Therefore, the larger the deformation is, the larger the force, right? So here the force gets to the largest because here it suffers the largest deformation, but here the force is smaller because it's closer to its original position, and here the force is smaller, and here the force is 0, right? Therefore, we see the force is actually proportional to its deformation. So how to describe this deformation? We use this concativity. Okay, the concave of this shape of this wave, which is exactly described by the second derivative of x. Okay. So which means more concave this form is, the larger the force. Okay. And when it's more flat, or when it's more like closer to this initial position, there's no force. Therefore, if we use F as this expression, we write this here, right? And we can, it's not equal, but it's proportional. Okay, proportional to m. M is a constant, and times the second derivative of t. Okay, so this is of the same form as here, but this is just an intuitive expression of why wave equation takes this form. The main problem is that how do we know this is proportional, right? It's not necessarily proportional. It can be of the square relationship or log. It's not necessarily linear relationship. But here, because we are only given an intuitive explanation, we assume this is proportional. Therefore, we easily get an intuitive explanation of the wave equation. Okay, so for a better illustration or a more precise model, yeah, I recommend you to read those two sources so that you know how wave equation is really like derived. So here another thing is, what I'll talk about is the linear acoustic. So the linearity is a basic property of the sound waves, and it's very fundamental and very important. Okay. So small amplitude phenomena can be described to a good approximation in terms of linear algebraic and linear differential equations. So the wave equation we just saw here, it is actually called a linear partial differential equation. Okay. So there is a linear relationship. And what is linear? Mathematically speaking, it means when you add two things together and you transform it, it's equals to the sum of the transformation. So to state it more plainly, it actually refers to the superposition principle, which means the net displacement caused by two or more waves is the sum of the displacements which would have been caused by each wave individually. Okay, so as we saw before, for example, if we have a wave produced by guitar, okay, if you remember the video we just watched, and there's another wave produced by piano. Okay, so the piano has a different kind of wave, but maybe they have the same pitch, maybe not, but there are two different waves produced by two different sound sources. Okay, so the guitar and piano are two different sound sources, but they are vibrating at the same time. Therefore, when they propagate in the air, they will actually meet each other. Okay, they will meet each other and they will mix with each other. But the problem is how they will mix. Okay, so if we don't have this superposition principle, let's say these two waves might interfere with each other. Therefore, we cannot, when they add together, let's say when they meet each other in the air somewhere, it produces a new waveform like this. If they interfere with each other, then from this new waveform, we won't distinguish the guitar and the piano back forth, okay? Because they interfere with each other, we cannot tell what this sound was made. But if we have the superposition principle, actually when they meet each other, they simply add together, okay? It's just a simple numerical add. Therefore, this new form is equals to this form and this form. This simply superposed upon each other. Therefore, we can still clearly tell 8 sound sources easily, okay, the guitar and the piano. So this is what the linear system means, and this is what the superposition principle is. And small amplitude phenomena means your wave is of very small amplitude. So in most cases, for the musical phenomena, it's always small amplitude. Therefore, it's okay to describe most I would say most like musical instruments or musical phenomena use the linear acoustics. But there are also like non-linear acoustics, which will be much more difficult and complicated. Okay. So this superposition principle means, right? So in addition, the behavior of a wave can be analyzed by breaking up the wave into components. The Fourier transform breaks up a wave into sinusoidal components. And Fourier transform is also a linear transformation. So the linearity actually gives us a lot of convenience when we decompose and analyze these sound models, okay? And also, the reason why when we're hearing like, you know, sound, a mixed sound with different sources, like now you're hearing me, I'm talking and maybe there's some background noise and you can still distinguish with them pretty well, partially because of these superposition principles, okay? So that it's not very complicated. But yeah, if the nature doesn't give us the superposition principle, I guess maybe your auditory structure can also evolve, right? Can also evolve some other structures that help you to distinguish different sound sources. So you never know what will happen, right? But whatever. So this is the wave equation here, and there's a general solution. So actually, although I'm describing those things using, you know, formulas, equations, I think the more important thing is the intuition, or what the formulas means, or intuitively how to understand those things. This is what my purpose is, to introduce you with those things. So here, we won't prove that this is a general solution to this wave equation, but we can actually give a very simple test of, right? So you see this is a solution. So this is a solution of this equation. So when we compute the second derivative of t of this formula, right? We can see there is actually a square. Okay, the second derivative, you take two derivatives on this formula, there's square, c square up, and this is f of the second derivative. And here is also a c square, right, of g second derivative. And on the right-hand side, when you compute the derivative of x, it will only be f plus g, okay? There is no coefficients because there's no coefficients between bp4x. Therefore, you can easily compare those two expressions. You can see this is correct, right? When you multiply this c square here, you get this exactly same expression for those two expressions. Okay, so we can easily test that this solution is actually a solution of this wave equation, but we won't prove that this is a general solution. But there is proof that this is indeed a general solution. Means general solution means all the solution of this wave equation actually observe this kind of expression. Okay. So besides this, how do we understand these quantities? Okay. So this is quite interesting because you can see here, actually our wave equation is decomposed into two different expressions, right? So actually this describes a sound wave propagating to the right. This is describing a sound wave propagating to the left. So you can see here, so f and g are arbitrary functions. So you can see for any wave equation, we can decompose this wave into two sound waves, which is traveling to the right and traveling to the left. So this is a one-dimensional sound model. Okay, this is one-dimensional because there is only x, x is one-dimensional. There is not y and g, or y and z. So in this one-dimensional model, sound wave, for any of the wave equation, here it will produce a sound wave from. So this is the initial position. After this, it will produce a sound wave going to the left and going to the right. Okay, so this is the general solution, and this is the general shape of wave that will be produced by a sound source. So for any sound source, one-dimensional sound source, there will be two waves propagating to the right and to the left. Okay. So when we give this initial value problem, we see when t equals 0, right? When t equals 0, the wave equation of this is of this shape, and the derivative is of this shape, and we can derive this D'Alembert formula. Okay. So this expression is not that important here, but it will definitely assist you to understand other concepts. Okay. So here, let me see the time. We still have some time. So here is a video that gives you some animation here. Okay, it shows the moving, or how to the visualization of this D'Alembert formula when you have initial excitation of the sound, and how the wave is produced and how it propagates. Okay, so let's watch this.
It's finally time to look at some specific examples of solutions to the wave equation. What we're going to do here is use the D'Alembert formula that we derived in the last video, and basically plug in different values for the functions f and g so that we get the solution to this initial value problem. And then we'll look at the solutions, decide if they make sense. Our first example will be pretty standard. We'll take f of x to be basically a step function. Let's call it box of x. And that'll be a function which steps up to the value of 1 for x between -1 and 1, and it's 0 otherwise. For g, we'll take just 0. If you remember that f of x is like our initial position for the string, and g is the initial velocity, this is like physically like stretching the string into the shape of a step function, which looks like this. It is 0 until it reaches the point -1, then it steps up to 1, and then it becomes 0 again. So it's like stretching the string into this shape. You can think of these jumps as being just very sharp stretches, and then just releasing it and seeing what happens. So what does D'Alembert's formula say will happen? Well, the g part is 0, so we don't have to worry about this integral. So we'll just have a sum of two f's. F is this box. So we'll have u of xt equals 1/2 box of, let's take c equals 1 just to be simple, box of x plus t plus 1/2 box of x minus t. So what is this? Well, it's a sum of two waves, one traveling to the left and one traveling to the right. Both of these waves have the same shape as the original guy, but only half the height. So these are half height boxes moving to the left and the right. I should say two of them. All right, I made an animation in Mathematica. Let's take a look. So what we're looking at here is the graph of u at the initial time, t equals 0, which is the same as the picture that I drew down here. And as I play the animation, you'll see the two half-height boxes move away from each other at the speed c equals 1. So at the initial time, you see that the two half-heights add together to be a total height of 1.
Right. So you can see in this animation, the waveform when it's so the initial position is this box function, right? And this after the release of this position, it produces two traveling waves to the left and to the right. Okay, it follows the description of the formula.
One, but then they start moving apart. Now, if you think about it for a minute, you realize that the fact that I used a box function here is really just irrelevant. If G is 0, then the D'Alembert solution will just be this 1/2 times the combination, the sum of the two f's, one moving to the left and one moving to the right. So really, whatever initial profile I start out with, when I let the wave equation do its work, I'll just see two half-height f's moving apart in different directions. All right, let's do another example. Just in case you think now that taking G to be 0 is just super boring, let's take f to be cosine x. And you'll see that actually something kind of interesting happens. So our initial shape is just cosine x, and then the D'Alembert formula will say that u must be 1/2. Let's take c equals 1 again. Cosine x plus t plus 1/2 cosine x minus t. All right, so just two cosine waves moving to the left and the right. Let's see what that looks like. So here's the animation. We see the initial profile of just cosine x, and let's see what happens when we let the wave equation do its thing. So it's a standing wave. Maybe you expected that, maybe you didn't. It certainly doesn't look offhand like a sum of a wave traveling to the left and a wave traveling to the right, but that is what it is. In fact, if you remember your trig identities and you look up the sum identity for cosine, you'll see that this in fact is equal to the cosine of t times the cosine of x. And that looks a little bit more like the graph that we were looking at. It's the cosine x multiplied by this cosine t, which is making it oscillate back and forth. Since this is kind of an interesting example, I made another animation where we see in solid black the original function u, and in blue we'll see the left moving wave, and in red we'll see the right moving wave. Now the black line is the sum
So this is the standing wave.
of the two, so it's the combination of the heights. So you see how this one standing wave can be a sum of two traveling waves moving in opposite directions. Okay, we've looked.
Okay, so I think this is the end of our lecture today. Thanks for coming. The materials might be a little bit demanding, but I think it gives you a basic introduction, and it gives us a more like smoother experience when we talk about musical instruments and the physical modeling and etc. So if you have any questions, you can ask me. So let me stop the recording now.